All right, here is the circuit from the test. So the first thing that we're going to want to do is take this first part of the circuit over here that's in parallel and really just reduce that down into a single resistor. So that's a pretty simple calculation. We can just use the rule for reducing resistors in parallel. So 1 over, and I'm going to zoom in a little so that I can write a little nicer. So it'll be 1 over our total resistance here is we're gonna call it resistance 3,4. And this is just going to be 1 over resistance 3 plus 1 over resistance 4. We are given both of these values, so we can just plug them in pretty simply. So 1 over resistance 3 is 10, and plus 1 over resistance 4, which is 15. So 1 over 15. All right, common denominator, easiest one is probably going to be 30. So this is equal to 3 over 30 plus 2 over 30. This gives us a pretty nice number. It's just 5 over 30. So that equals 5 over 30, which we can reduce to 1 over 6. So now that we have this, we can flip our fraction and get our resistance 3,4. Because remember, this is resistance 1 over 3,4. 1 over our 3,4. So if we really want the resistance 3,4, we need to flip our fraction and we get that R34 is equal to 6. And of course we measure this in ohms. And we can put this in a nice colored box because we might want to refer to it at some point later. So what we have done here is we have taken this circuit and we have now reduced it. So let's duplicate this and bring it over here and change it into what our new circuit's going to look like. So we've gotten rid of all this. This is now gone, and we have reduced it into a single resistor, which looks something, whoops, I'll do it with black, looks something like this. And now we've simplified our circuit quite a bit. We now have 3 of these resistors in series, which is pretty easy to work with. And let's just throw some labels on this. So this resistor is just R34. So there we go, R34, which is equal to 6 ohms. So R34 equals 6 ohms. So now that we have these 3 all in series, we can find the equivalent resistance rather simply by just adding them all together. So we have 30 plus 6 plus 24. So let's write all that in. And again, we're going to use the same notation that we did before. If we're combining resistors, we're just going to make the subscript just the subscript of all of the numbers that we are combining together. So in this case, we're combining together 2, 3, 4, and 5. So we'll call it R2, 3, 4, 5. And R2, 3, 4, 5 is just equal to R2 plus R3, 4 plus R5. Which is equal to R2 is 30 ohms plus, then R34 is 6 ohms plus R5, which is 24 ohms. All of that adds together to give us 60 ohms. So that is our new equivalent resistance. So again, we can take this number and let's put it in a nice colorful box in case we want to refer to it later. Actually, I'm going to put the label on it first. On this bottom row are 2, 3, 4, 5. And then I'm going to put a box around it. So there we go. And now again, let's take our circuit and duplicate it. We'll move it down here. And we're going to change it to be what it is now. So all of these circuits have now been reduced into one. So we will erase all of these things because we have found an equivalent resistance for them. And we just have this one resistor that runs something like this. There we go. And that's R2345. So we should label that appropriately. R2345. Last thing that we can do for our resistance combinations is to take our R1 and our R2345 and find the R total for the entire system. This is all of our resistances all together, so we can just call it RT. And again, we're going to use the law for parallel, just like we did for the first circuit combination that we did. So for parallel, we're going to have 1 over RT is equal to 1 over R1 plus 1 over R2, 3, 4, 5. Fill in the numbers. R1 is 15 ohms. I should probably write the numbers on this diagram as well. R2, 3, 4, 5 is equal to, it was 60 ohms. So filling in our numbers, we have 1 over R1, which is going to be 1 over 15. 1 over 15 ohms plus 1 over our R2345 is 60 ohms. Again, we want a common denominator. We could find something really complicated by doing 15 times 60, but we could also just make it really simple by going straight to 60, because 15 can get us to 60 pretty easily by just multiplying by 4. So multiply our first fraction by 4, and we get 4 over 60 ohms plus 1 over 60 ohms for our second term here. And then we can just add these fractions together and get 5 over 60 ohms. You can reduce this fraction by just dividing both sides, or both top and bottom, by 12, or sorry, by 5, which will give you 12. So it's equal to 1 over 12 ohms. Now remember, this is 1 over RT. This is not RT, this is 1 over RT. So in order to get RT, we need to flip our fraction. So again, we're going to do that, and that gives us RT is equal to 12 ohms. Because of course, if we do RT over 1, that's just RT. Dividing anything by 1 doesn't change anything. So this is our total resistance. We can put this in a nice box, very bright, so that we can find it later in case we want to do that. Okay, so now we have reduced our circuit, and again, let's rewrite it so that we can really see what's going on. So let's take this, and we'll duplicate it, drag it down over here. Sure. That'll work. Okay. So zooming in over here. All of this has now been reduced into 1. So we can get rid of all of these resistors. We can keep our battery though. Just reduce these into 1 resistor. And our total resistance here is just 12 ohms. So I'll do this. Whoops, I'm on red again. Go back to black. Do this, come down, make a little squiggle for my resistor. And there we go. And this resistor I can label as 12 ohms for RT. So RT is equal to 12 ohms. Now we can really start looking for everything that we care about. We're looking for IS, I1, I2, I3, I4, I5, and then our voltage 1, 2, 3, 4, and 5. The first thing that's going to be fairly easy to find is going to have to be the voltage would be whatever we gain we have to lose, right? So our voltage gained 24 here needs to be our voltage lost here. But we don't care about VT. We could calculate VT, it's just 24. But we'll use that later on in our problem. So let's write it down anyway. So we have that RT is equal to 12 ohms, and we know that VT is equal to 24 volts. So VT is equal to 24 volts. Now again, this isn't one of the things that we're solving for, but it's going to act as kind of an intermediate step. And what that's going to do is help us get to IS, because IS can be calculated by using V equals IR for this resistor. And the reason that we can do that is because we have series. There's only one resistor, so it's series, I guess you could call it that. And the current has to be the same at every point. There's only one path. So anything that comes in must come out. That's Kirchhoff's current law, right? And we can just solve that with V equals IR. So let's do that. So V equals IR, in this case, we're dealing with VT. VT, oh, and let's put that in a red box, just to keep doing the same thing. Red box right there. There we go, looks beautiful. So VT is equal to IS, I the whole system. So is equal to IS RT. We want to solve for IS, so we're just going to divide by RT. VT divided by RT is equal to IS. And then we can just plug in our numbers. VT is 24, and RT is 12, so it'll be 24 divided by 12. So that's 24 volts divided by 12 ohms. And that is equal to our IS. And the value that we're going to get here is 2. And current is measured in amps. So 2 amps is our IS. This is the first thing that we have that we can actually cross off. So coming up here, IS, done. So now we know that initial current. And again, let's put a box around this just so that we know what it is. We're going to find a lot of stuff here. And it will become very easy to lose track of things if we don't be careful about it. So IS, 2 amps. Now if we look back at our previous circuits, we have this one up here, which is what we started with, right? So we have IS, which is 2 amps. So 2 amps has to be here and here. But as soon as we come here where we could split, then we don't really know what we're doing. So that's a bit of a problem. We can't use IS over here, can't use IS here, at least not quite yet. So let's see what else we could possibly do. We could look at one of our other simplified circuits, this one. Again, we have IS splitting, and we don't have any equivalent voltages here either. So that's a bit of a problem. What other circuit do we have? We have this one. We have this one over here. Now our current is going to split, but we only have 2 paths for our electrons to take here. And we know that in parallel, the voltage drop has to be the same. Now that's also true up here, But the problem with doing the voltage drop here is that you have a voltage drop which is just through a single resistor, and this voltage drop is going to happen through 3, so it makes it far more complicated to calculate. So this is going to be where we want to look at initially. So we know that we need to drop some voltage here, and we need to drop some voltage here, and it needs to be the same amount, because whatever the electrons that travel through here drop, the electrons that travel through here also need to drop. That's just Kirchhoff's voltage law for things that are in parallel. All right, so how much are we dropping? Total voltage is 24. We need to drop 24 here, and we need to drop 24 here. So V1 is 24. And V2345 is also 24. Now V1 is actually one of the values that we were looking for. So if we write that in, again, we can cross off one of the things that we have, which will be somewhat helpful. So let me just find where I am here. $60 ohms. Where am I? Ah, there I am. All right, so coming down here. From this, we can determine that our voltage drop through each of these must be 24 volts. So V1 is equal to 24 volts. And also we have that V2, 3, 4, 5 is equal to 24 volts. And again, let's put these things into some boxes so that we can keep track of all the things that we have managed to find. So far, we have found IS, and we just found V1. So that's nice. Now this means that we can find I1 and we can find I2345, just using V equals IR again. So if we use V equals IR on this, well, let's just work through the math. So V1 is equal to I1R1. The thing that we're looking for here is I1, and we have R1. It was given in the initial question. R1 is just 15 ohms. V1 we just listed, so let's rearrange and solve for I. V1 over R1 is equal to I1. V1, 24. 24 volts divided by R1, 15. 15 ohms is equal to I1. All right, this isn't the nicest number, but we could do a little bit of simplification. We could divide this by 3 and divide this by 3. So to simplify our fraction down, we could do 8 volts over 5 ohms equals I1. 8 over 5, that's going to be 1 3/5, so 1.6. So 1.6 amps is equal to I1. Again, this is a piece of information that we want. We'll put it in a nice red box. And then we will move on to the next part of the question. So looking up here, for the things that we want, we just found I1. All right, so what's up next? V equals IR. We can also apply over here. Now, this is going to give us the I2345, which again is not one of the things that we are directly looking for, but it's going to be a nice intermediate step in order to help us acquire some of the other values like V2, V3, V4, V5, all of those ones, and also the I's as well. So let's find our I2345. So coming back down here, we have V equals IR. So V 2, 3, 4, 5 is going to be equal to IR for 2, 3, 4, 5. So equals I 2, 3, 4, 5 times R 2, 3, 4, 5. A lot of subscripts going on here. Looking for I, divide both sides by R. Divided by R 2, 3, 4, 5. Then divide this one by R 2, 3, 4, 5. This one cancels over here. And then we can just plug in our numbers because we have solved for I. So V2345, we have that somewhere. V2345 is 24 volts. Let's fill that in. 24 volts divided by R2345. What was that? That was 60 ohms. So we can fill that in as well. Equals I 2, 3, 4, 5. 24 over 60. So what can we do here? We can divide by 4, or we could divide by 6. 6 seems like a good number to divide by. Let's do that. 4 over 10 amps equals I 2, 3, 4, 5. And we can reduce that even a little bit more. We can divide this by 2 and get 2 over 5. 2 over 5 amps is equal to I 2, 3, 4, 5. That's a big 4, but we'll go with it. And that's 0.4 amps, in case you really like decimals. So it's another number that we can draw a nice box around, because we are probably going to need it later. Okay, so we found a bunch of stuff, which is nice. We just found I1, and we found I2, 3, 4, 5. So I1 is one of the things that we're actually searching for. We've already crossed that off, so that's nice. V2, 3, 4, 5, and I2, 3, 4, 5. Those are really the things that we're going to be more interested in. So here we have I2, 3, 4, 5, and if we look back over at this, our I2, 3, 4, 5 is the I that's going through all of these. Now the current at any point in this part needs to be constant, because there's only one path. Once we've passed this junction, we only have one path to go around. So whatever our current is for 2, 3, 4, 5 is going to be the same as the current for 2, which is going to be the same as the current for 3, 4, which is going to be the same as the current for 5. So we could say that. Let's do that right over here. Okay, so coming up to this. We can say that R2, actually I think I'll start with writing it out like this. So R2, 3, 4, 5 is equal to, oh sorry, not R, I'm talking about current, not resistance. I 2, 3, 4, 5 is equal to I2, which is equal to, now this resistor over here is a combination of resistors. We can't say that it's equal to I3 and I4 because when we break this down, it's actually in parallel. So we have to keep it as I34. So this is equal to I34, which is equal to I5. Now some of these numbers we're actually looking for. We want I2 and we want I5, so we can cross those off of our list as soon as we have our value. Now our value for this we found down here, it's 0.4 amps. So filling in all of this, that is 0.4 amps, which is a new piece of information that we could put into a nice orange box. And there we go. So now what have we found? We have found IS, I1, I2, and I4 we just, or sorry, I5 we just found. We have found V1. So we need V2, 3, 4, 5, and I3 and I4. We can't find I3 and I4 until we break this resistor back into its two parts. But we can look for V2 and V5 because we have the current of those and we also have the resistance. So let's do just that. V equals IR. V2 equals I2 R2. I2, just found it, 0.4 amps. R2 is given in the question. R2 is 30 ohms. Multiply that by 30 ohms. Equals 0.4 times 30. That's 2 over 5 times 30. Which is exactly the same as saying 30 divided by 5 is 6 times 2 gives us 12. And this is volts. Now that seems like quite a bit, but that's fine. The first one is going to drop 12. We would expect that across these, we would end up with them also summing to 12. Because if we take this path here, we need to drop a total of 24. And this actually makes quite a bit of sense because this resistance here is 30, and these two resistances here add up to 30. So we would expect that these two give us 12 volts as well. So let's do V5. Actually, let's do 3, 4. Let's do V3, 4. Just makes sense to do them in order. So V3, 4 is equal to I3, 4, R3, 4. Which equals I3, 4 is right here. All right, 0.4 amps. Let's keep it as that 2 over 5. 2 over 5 amps times R34. R34 we calculated before, it is 6 ohms. Multiply this by 6 ohms. This is equal to 2 over 5 times 6 is 12 over 5. 12 over 5 is 2.4. 2.4 volts. And let's draw some nice red boxes again. 12 volts, that is V2. And 2.4 volts, this is V34. V34. And the other one was V2. V2. All right, last one here is our 2 and 3, 4, so we need to do 5. Let's go down, actually. V equals IR again, so V5 is equal to I5R5, which is equal to I5, 0.4, 2 over 5. 2 over 5 amps times our resistance for number 5 is up here. It's just given in the question. It's 24 ohms. 24 ohms. And this number doesn't look like it's going to end up super nice. 2 times 24 is 48. Over 5 doesn't give us a nice round number. So equals 48 over 5. And this is volts. So this is 9 3/5. 9 3/5 is going to be 9.6. So 9.6 volts. So equals 9.6 volts. This is V5. And we can put a nice orange box around this one as well. So now we have found a few more values. V5, 9.6, V3, 2.4. Now we can do a little check here. And let's just do it in another color. So we have all of these here, and we know that if the electrons travel through this path, they need to be losing 24 volts. So we have it losing 12, and then 2.4, and then 9.6. So our voltage between all of these should add up to 24. 12 plus 2.4 plus 9.6. Well, 9.6 plus 2.4, that's 12. And then another 12 gives us 24, which is just a quick check. We could write all that out, which we probably should. So Vs is equal to what was it? 2, 3, 4, and 5. 2 plus V3, 4 plus V5. We're going to do a little check here. Question mark. So let's do a left side, right side check. Left side. Left side is equal to Vs is just the 24. Right side. Quick right side check. V2 is 12. V34 is 2.4. And our V5 is 9.6. So let's fill all that in. So we have 12 volts. This is in volts as well. 12 volts plus 2.4 plus 9.6. And that is, in fact, equal to 24 volts. So that means that our left side is equal to our right side. So far, so good. We have what we would expect. So now what did we just find? We just found our V values for V2 and V5. Now, we need to solve for 3 and 4. It's the last things that we are missing. We're missing I3, I4, V3, V4. And now we can do that, but in order to do that, we need to break it back down into its original parallel form. So we need a voltage drop here of V34 is 2.4. So let's look back at our initial thing. So no matter which path we take here, we need to drop 2.4 volts. So the current is going to split. We're going to get different values for current here, but we have the voltage. It's 2.4. We just calculated that over here, 2.4 volts. So if we have our voltage, then we can calculate our current because we are given the resistance within the problem. So again, we're going to apply V equals IR. But we're going to do it over here with our original circuit. So all of this breaking it down and reducing these things really all comes back to our original circuit in the end. So this is what we're going to do. Once I get positioned here properly. And change my color back to black. And we have v equals IR. So we are looking for R3, or the currents for 3 and the current for 4. So I3 and I4. So V3 equals I3 R3. We care about the current. That's the thing that we're missing. Let's solve for it. V3 divided by R3 is equal to I3. V3 was 2.4. 2.4 divided by R3, 15. This is equal to I3. Okay, so this is some not super great number. I'm just going to calculator this one. See what we get. 2.4 divided by 15. 0.16. So 0.16. And if we fill in all of our, that's a terrible 6. Let's make a better 6. 1.6. So this is in volts, this is in ohms, and our current is in amps, which is equal to I3. Cool. So 0.16 amps is equal to I3. Now the total current through this section we figured out earlier. That was all of our I's over here, 0.4. So we should expect that our two currents, our current 3 and our current 4, add up to 0.4. And we can do that check after we calculate current 4. First, let's put a box around this so we don't lose track of it. And then we can calculate our I4. So our I4 we'll just do right underneath of this. Let's come back over here. So V equals IR, V4 is equal to I4, R4. Rearranging for I, V4 over R4 is equal to I4. And then we just plug in our numbers. Our V4 is exactly the same as our V3. It's 2.4 volts. 2.4 volts. And our R4, that is given right up here in the problem. It's 15 ohms. So we can just fill that in. Divided by 15 ohms. This is a V. So 2.4 divided by 15. And what do we get there? This is I4. Again, I'll type this in. 2.4 divided by 15 is equal to 0.16. Whoops, we made a mistake. What was our mistake? This was actually the value for R4. I plugged in 15 ohms here. Go, 0.16 again. And that's because I plugged in the wrong number, which means that really what we want to do down here is not plug in 15. We want to plug in 10. And then we'll just change all of these to 3s, because the calculation is exactly the same. So not R3, or not R4, we'll do R3. And then all of these 3s need to be 4s. Yeah. Okay, so that'll be lots of fun to fill back in. And I missed one right here. So this first one was actually V4. V4, R4, I4, I4, V4, R4, and then those numbers all work out, so 0.16. And now down here is where I'm actually doing my 3s. So I3, R3, V3, V3, R3, I3. So 2.4 divided by 10 is what I want, which should be 0.24. 0.24 is equal to I3. Should be an I3. Okay, so that's a nice example of how you can kind of catch mistakes. I knew that my total current needed to be 0.4, and from a brief check, I found that my 1.6 that I got up here plus my 1.6 that I got down here, it wasn't going to add up to 0.4. Now if I do a check, I would get that 0.16 amps plus 0.24 amps does in fact equal that 0.4 that I need. Now in terms of what I found, let's just go through everything. All that we were missing up until this point was I3, I4, V3, V4. We'd found all of these other ones. And we just found I3 and I4, if I put a label on that. So those are good as well. And the whole thing that I used here in order to actually calculate these was that the voltage for these two was going to be the same, which needed to be the voltage for R34. So R34 we calculated, or sorry, voltage V34 we calculated over here. And this V34 actually needs to be equal to V3 and it needs to be equal to V4. So let's fill that in. Equals V3 equals V4. And then we can put that in a big red box as well, because that is the remaining values that we need. So here's everything. I know it's kind of all over the place, but everything's in nice boxes so we can find it. We want IS, I1, I2, I3, I4. IS we found somewhere. Did we not put it? Oh, here it is. IS, 2 amps. 2 amps is IS. I1, 1.6 amps. I2 was found up here. I2 is 0.4. I3 we just calculated. It's over here, 0.24. I4 as well, up here, 0.16 amps. And the last one that we had was I5, which was also calculated over here, 0.4 amps. So that's all of our currents. Our voltages, we need V1 over here, 24 volts. V2 up here, 12 volts. V3 was over here. It is, we used it over here. We solved for it over here. V3 is the same as V34, which is 2.4 volts, and that goes as well for V4. And the last thing that we needed was V5, which we found down here. V5 is 9.6 volts. So that is all the things that we needed to calculate. This problem is now done. We could do a quick check, and then I guess we'll call it a day. So let's just check our currents over here. What I mentioned before is that I spotted this mistake because I did a quick mental check, but let's write it out. We would suspect that our I3 plus our I4 is equal to our I34. So let's calculate that real quick, and we'll do it in a different color for the check. So I3, 4 is equal to I3 plus I4. And we don't know if this is true, so we'll throw a question mark on it, do a left side, right side check. I34. What was our value there? I34 was calculated somewhere. I34 was equal to, here we go, 0.4. 0.4 is our I34. So left side is equal to 0.4 amps. Right side is equal to I3 plus I4. Now I3 and I4 are right here, 0.24 and 0.16. 0.24 amps, I kind of ran out of room, plus 0.16 amps. Try to make a better 6, 16 amps. And if we add those together, we do in fact get 0.4 amps. So we have that left side is equal to the right side, which is nice. Then we could do a bunch of other checks, right? We could check that our I234 is equal to I2, which is equal to I2, or I34, which is equal to I5. We check that if we really wanted to. You could check your total current through the system with the current total resistance. These are two major ones that I would definitely consider doing, but you can check anything else that you really want to in this system. But yeah, that's the circuit. So there's a bunch of steps, right? But each step is fairly simple. It's just V equals IR over and over and over again, and then every once in a while you need to apply one of Kirchhoff's laws, either Kirchhoff's voltage law when you are in parallel, or Kirchhoff's current law when you are in a series. So yeah, happy circuit solving. I will post this, and then you can see both the fixed image as well as the full video for it. Happy circuit solving.